Welcome to BTEC Revision. In today's lesson, we're looking at fluid dynamics. By the end, we should be able to calculate the volumetric flow rate of a system and calculate the mass flow rate of a system. The volumetric flow rate is the volume of fluid that passes a given point in a time. It's given by the equation volumetric flow rate equals volume divided by time. And the short form of this equation is V dot equals V divided by T, where V dot stands for volumetric flow rate, V stands for volume, and T stands for time. Now, looking at the units, time can be measured in seconds, volume is measured in meters cubed, and therefore volumetric flow rate is meters cubed per second. We can also write volume as area times displacement. So therefore the equation becomes area times displacement divided by time. And we can leave area as it is, and displacement divided by time we know is velocity. So we can write this as area times velocity. So the second form of this equation is volumetric flow rate equals area times velocity. Here we have a tapering pipe, which is a pipe where the gap changes in diameter. And we'll label the left side over here as 1 and the right as 2. If you look at position 1 here, we see we have a diameter which looks larger than the right side, position 2, and same thing with the area as well. So area 1 is larger than area 2. We can also see we have velocity v1 on the left side, and that's moving towards the right, and that's representing the flow of water or a liquid. And as it's going through, it will have to change its velocity. So it would either increase or decrease depending upon the variables, which we'll look at now. So V2 would be different to V1. So on the left side, we have V dot, which represents the volumetric flow rate. Okay, we'll label that as 1 for position 1. And on the right, we'll do a similar thing, V dot 2. And the key thing is about this lesson is that these two values must be equal. Okay, V dot 1 must be equal to V dot 2. Now, looking at position 1, you can also say that the area 1 times the velocity 1 is equal to area 2 times the velocity of position 2, the water at position 2. Now, looking at the mathematics here to see if V2 is going to increase or decrease, we can write our equation from last lesson, A1 V1 equals A2 V2. And rearranging this for V2 would give us a value V2 equals A1 V1 divided by A2. So looking at what's happening here, what would happen to the velocity if the area is decreasing here, right? So the area is decreasing. So if that's decreasing, that means to balance this equation, the velocity must increase. So in this case, V2 would be increasing, which would make sense. If we narrow the pipe, the water will still need to get through and it will go through faster, okay, in order to balance the volumetric flow rate. So V dot 1 must equal V dot 2. Now let's try an example. Water is flowing through a pipe with a diameter of 10 centimeters. The average velocity of the water is 2 meters per second. Calculate the volumetric flow rate of water through the pipe. Now, the first thing to note here is that we have two different units. We have one in centimeters and one in meters per second. So it would be sensible to convert them into the same unit. So we'll change diameter of 10 centimeters to meters. So we divide by 100. to convert centimeters to meters. So that would be 0.1 meters in diameter. Now we can write down the equation. We have v dot equals, now there's two forms. The one we need to use is the one that has velocity because we have the value for velocity. So that's area times velocity. No, the capital V is used to represent volume and lowercase v is used to represent velocity. So try not to get those two confused. The smaller one is velocity. So we have velocity, okay, that's 2, but we don't have area. And if we're looking at a pipe, normal pipes are cylindrical, and therefore the area we want is for the area of a circle. So this is the area, and the area is going to be equal to, if you remember from mathematical techniques, pi r squared. Okay, so therefore that's pi times the radius. We know the diameter is 0.1, so the radius is 0.05. And if we square that times by pi, it gives us the area. Okay, so remember the radius is half the diameter. So that's 0.05 squared times pi, and that would give us a value of 7.854, and that would be in meters, and don't forget the times 10 to the negative 3 meters squared. Okay. Now we can plug this in to get the area. So it's this value times the velocity. So it's 7.854 times 10 to the negative 3 times 2. And that would be equal to 15.71 times 10 to the negative 3. And the unit is going to be meters cubed per second. And look at mass flow rate, which is the mass of a fluid that passes a given point in time. The equation for this is mass flow rate equals mass divided by time. The short form for this is m dot equals m divided by t. And the units, mass is measured in kilograms, and time is in seconds. So therefore, m dot, or mass flow rate, is kilograms per second. And if we remember from a previous lesson on density, we know that density, rho, equals mass divided by volume. So we can rearrange this for mass. Mass equals density times volume. So therefore, if we replace this equation, m, with rho times v, we'll have rho v divided by t. And we know that v divided by t is volumetric flow rate. So therefore, that becomes rho v dot. Now, let's try this example. A fluid with a density of 800 kilograms per meter cubed is flowing through a pipe with a diameter of 0.2 meters at a velocity of 5 meters per second. Calculate the flow rate of the fluid. The first thing we can do is write down the equation for mass flow rate, which equals rho v dot. And we know the density, that is 800 kilograms per meter cubed. And we need to work out the volumetric flow rate first, which, if we remember, equals the area times the velocity. So we have the diameter, and it's a pipe, so we'll assume a cylindrical pipe, so therefore the area is going to be pi r squared. So we'll have to calculate that first. So area equals pi r squared. We know the diameter is 0.2, so the radius is 0.1. So that's 0.1 squared times pi. Yeah, we'll just leave it as pi over 100. And the unit for that is meters squared. So that's fine. We leave that as it is. Okay, now we know the velocity as well. That's 5 meters per second. So we can plug that in to work out the volumetric flow rate. So the area times the velocity, okay, which we have is 5. Plug that in there. So that's going to give us a value of, so that's pi over 100 times velocity, which is 5. And then that simplifies to pi over 20. And the unit would be volumetric flow rate, which is meters cubed divided by seconds. Okay, now we know that, we can plug that in to the very first equation. So the density is 800, so that's 800 times the volumetric flow rate, which is pi divided by 20. And it gives us the value of 0.125 times, let's say, 7, we'll add, times 10 to the power of 3, and we'll simplify that. So that's 125.7. And the unit for that is kilograms per second. Now pause the video here and attempt this exam question. Water is being pumped for crops in a farm with a velocity of 5 meters per second through a gradually decreasing tapered pipe. The pipe's initial diameter is 100 millimeters, and the water needs to exit the pipe at 10 meters per second. Water has a density of 1,000 kilograms per meter cubed. Calculate the diameter to which the nozzle must be tapered in order to achieve this velocity. So the first thing we should do is write down the values that we have. And even if you don't know straight away what we need to do, if we start by writing down what we have, then we can work out what we don't have. And from there, we can sort out a solution. So the first thing we'll write down is the diameter, initial diameter. So we'll draw a little picture, okay, which is 100 millimeters. And if we convert that into meters, we should get a mark already. So that's 0.1 meters. So we'll write 100 millimeters equals 0.1, and that's the diameter. Okay. Right. And then we have the velocity as well. So we can draw that. So that's 5 meters per second. And so it needs to exit, and it's gradually decreasing like that. And the exit velocity needs to be at 10 meters per second. So the question is, how much should the diameter be? So we can, first of all, write down the equation, so volumetric flow rate, which is equal to the area times the velocity. Now, of course, we don't know the area, but we know the diameter, and we'll assume it is a cylindrical pipe. So the area equals pi r squared. So that's pi times 0.1 squared. So that would be an area of pi over 100. The velocity we know is 5. So that is an area of pi over 100. Velocity is 5, so that's times 5. Because that's the volumetric flow rate at the left side. And this should be equal, so that's for 1. And this should be equal to the volumetric flow rate on the second side. And if we work that out, that's going to be area. So that one's 1. And this one will be 2 times the velocity of 2. So that's the value. Area, we don't know. So we will need to calculate that because it's asking for diameter. And if you remember, area equals pi r squared. So if you can work out the area, we've got the radius, and from the radius we work out the diameter. So we don't know what that is, so we'll leave that as a2. We know the velocity is 10, so times 10. Okay, so we can put these together, and that will give us 10 a2 equals 5 pi over 100. So if you divide that by 10, that will give us a value of a2 equals 5 pi divided by 1,000. Okay, and working that out gives us a value of 0.0157. That'll be meters squared. So that's the area. But from that, we need to work out the diameter. So we'll work out the radius first, and we'll plug that into this equation. So we want to rearrange that for r. So r equals a, well, r squared equals a divided by pi, and you can square root everything to get r. So r is equal to area, so this value here, divided by pi, and dividing that by pi, and then square root our answer, gives us a value of 0.071 meters. And then we can times by 2 for the diameter. And then therefore the diameter equals 2 radius, which is equal to 0.141 meters. Okay, so the answer is diameter equals 0.141 meters, which is equal to 141 millimeters. And that's the end of the lesson. If you would like to boost your grades, visit us at btechrevision.com with lots of quiz questions and lots more resources available. See you next lesson.